I will present tidal tomography of the Venusian atmosphere. But first, a little bit of context. So yeah, next slide, please. Thank you. So at the surface of Venus, there's a little bit of solar radiation that is absorbed, and that's enough to create a tide that moves the sun. And that tide, with an overpressure and a pressure, creates a torque that prevents Venus from being tidally locked. So that's something that was recognized by Gold and Sauter decades ago. Next slide, please. So this tide is very important because this is you need to understand that tide to understand the spin of Venus and its evolution, the current state of the spin of Venus. And yeah, in the next slide, this is the estimates from analytical models of the amplitude and the lag of this tide as calculated by Dobrovolskis and also by LeConte later in 2015, where he estimated the amplitude and the lag for exoplanets, but also for Venus. And you can see that the amplitude for Venus is much lower than clear sky conditions with 1 or 10 bars, but nevertheless it still exists. And it's something that we can measure and that gives a lot of information. However, those models are very simple and they do not take into account topography, at least for the Dobrovolskis model. So in the next slide, please. We used a state-of-the-art Venus GCM, the Institut Pierre-Simon Laplace GCM that many talks after mine will talk about. And the important fact about this GCM is that it takes into account the topography from Magellan at 96 by 96 latitude grid. That gives us roughly a grid size of a few hundred kilometers at the equator. And that's enough to resolve the atmospheric dynamics for the large scale circulation. So next slide, please. So here is the result from the model and the current version that we are using from Garate-Lopez 2018, the version that we are using for tidal tomography. You can see the zonal winds as a function of altitude measured by the In situ Pioneer Venus probes and comparing the previous and after implementation of Garate-Lopez. So what Garate-Lopez implemented was a varying cloud top, a cloud top that varies altitude that varies with latitude. And what's interesting, in the next slide, please, you can see the impact it has implementing a variable cloud top altitude it has on this thermal tide. Here on this plot, you can see the surface pressure anomaly, but you see we have removed the hydrostatic component as a function of time and longitude at the equator. So the sun apparent motion is moves towards increasing longitude with time. And in the red and in the green versions, you can see how it changes not only the amplitude of the tide, but also all the other waves that propagates towards negative, westward negative longitude. And so that's an important fact that to take into account all the atmospheric dynamics that will impact the tide. So next slide, please. Here is another view of the same GCM, the simulated thermal tide. And here are snapshots where you can see how the overpressure and underpressure moves around the planet. So it's quite different from Dobrovolskis because here we take into account surface dynamics and topography. And so this was a work done by Bruce Beals and myself and my other co-authors. So next slide, please. In which we estimated that the gravity signal of this tide can or will be measured by future missions in theory. So the thermal tide here is in purple, and it's below the error of the existing data set of gravity. But with future mission configuration, we might be able to get the thermal tide up to spherical harmonics degree number 30. So in the future, we might be able to measure the gravity changes by this tide. So next slide, please. So here is the impact it could have. I plotted the angular momentum density from Pioneer Venus that peaks near 20 degrees, 20 kilometers of altitude, indicating that there is a large reservoir of angular momentum for the super rotation. And on the right is a simulation by the GCM showing the atmospheric density that decreases with altitude and the standard deviation accounting for the fluctuations over many solar days. You can see that in the first few kilometers near the surface, the impact of this thermal tide that is one order of magnitude higher than the rest of the fluctuations that exist throughout the atmosphere. But by measuring the gravity signal, not only we have an indication on the thermal tide, but also all the tides that exist above in the cloud deck. Uh, and that could be of an indication of what's happening in this reservoir of angular momentum. So not only with gravity we can measure the surface pressure, but we will have information on the whole atmospheric dynamic. So a gravity measurement will have will be a possibility to measure globally the surface pressure and the structure of the atmosphere, which is something that is very interesting for Venus given how difficult it is to access the surface. So next slide, please. So this is the motivation of tidal tomography to measure the thermal tide. And the question is, if we have a measurement of the tide, how can we constrain our knowledge of the surface and the atmosphere? So in the next slide, we have identified four poorly constrained parameters in this GCM that we can inverse the problem to estimate those parameters by having a measurement on the thermal tide by tuning those parameters. So from top to bottom, we have the cloud top altitude, which I talked a little bit before. That depends on the latitude. We can also change the heating rate of the lower haze below the cloud deck, altitude 30 to 48 kilometers roughly. And because we don't know the nature of the haze, we can change. So can you go before? Yeah, we can modify the heating rate in the visible range to change the amount of heating of visible wavelengths that reach the surface and that change the amplitude of this thermal tide. Then we have little estimate on what's called the surface roughness. The roughness is the typical average size of the rugosity of the surface. Is it 1 centimeter pebble versus 1 meter boulders? And the size of the rugosity will impact the friction in the boundary layer and in turn have an impact on the surface winds. Another poorly constrained parameter is the thermal inertia, because we don't really know the nature of the ground, if it's what is the porosity of the ground, and that will constrain the thermal properties. So we're not seeing here that we can constrain the surface parameters that we just talk from a point of view of atmospheric modeling, and that those parameters will have an impact on the atmosphere, but we are not saying that we can constrain surface or geological parameters per se. That at this point is just something that is interesting for GCM modeling, and is something that is not constrained yet. So the next slide, please. Here are preliminary results of varying those parameters. On the top left, you can see the amplitude of the thermal tide. And in white contours are the topography. And you can see for the lower the altitude, the higher is the amplitude of the thermal tide in the reference run with nominal values. But if we vary the heating rate of the haze layer, of the thermal inertia, TI, of the roughness parameters, you can see the deviation from this reference run. For instance, with a higher thermal inertia of 50,000, which is very high and probably unrealistic, we have we reduce we have more heat transported toward the ground, and we change the whole amplitude of the thermal tide. But if we change things like the roughness parameters, we have very localized changes in the amplitude of the thermal tide. So in the next slide, please. One explanation is that the regional scale dynamics can explain a large a large part of the parameter sensitivity. In 2018, there was a first and only paper on surface dynamics of Venus that found that the surface dynamics are a combination during the day of westward motion and upslope winds, where during the night there is katabatic wind, that is the wind moving air downward the slopes. And the combination, the typical wind speed of at the surface are a few meters per second, and just by doing a back of the envelope calculation, of using the conservation of momentum, the typical gradient associated with those winds are 1 kilopascal, which is the amplitude of thermal tide itself over 1,000 kilometers. So taking into account those surface dynamics is important for assessing all the spatial patterns, complicated spatial patterns of the thermal tide. So next slide, please. So this is a preliminary result, and the next step toward solving the universe problem are to fully assess see if we can have a function of the amplitude as a function of all the parameters and characterize all the spatial patterns and regional dynamics. In the end, what we want to do is to introduce the new concept of tidal tomography for the next Venus missions, and also assess the potential landing site of interest for long-lived lander. Thank you.